In this video, we're going to take a look at informally analyzing the binary search and the linear search algorithms. And the reason why I say we're going to do an informal analysis is because algorithm analysis is this whole area of computer science that deals with determining the amount of time or the amount of memory, the amount of storage required to execute some particular algorithm. And associated with that is a lot of formalism. And I don't want to really get into the formalisms in this particular video. But I will say that there's two main methods for going about doing algorithm analysis. One is an empirical way, so we could go about timing how long it takes us to execute a particular algorithm on a particular computer system. Or we could maybe count up the number of operations, so the number of comparisons, the number of additions, the number of multiplication operations. So each one of those would have a cost associated with it. But with empirical analysis, we do have this drawback that it's dependent upon the speed of a particular machine. So if we were to run the same algorithm on a different machine that was, twice as fast or had twice as much memory, we may get very different results. And the same thing goes with the programming language we use. So if we were to move from one programming language to another programming language, then the number of operations, the number of additions, the number of comparisons, the number of multiplication operations may be very different. So that's really the drawback there with the empirical analysis. You really want to be comparing apples to apples and not have some sort of dependency there depending on what computer system or what programming language you're using. So with the analytical method, you really don't have those drawbacks. And with the analytical approach, we're looking at maybe picking out a particular operation that maybe dominates the algorithm and finding out how many times that particular operation is executed. And we really don't even need to know the count precisely of how many times the dominant operation executes. We can just express it as a function of the input size. So take, for instance, the linear search. We know in that case, the comparison is really the dominant operation that's going on. And it may be the case that we have to compare every single element in that array before we find the thing that we're looking for. So we can see in that case that does change depending on how many elements we have to search through. So if we only had 10 elements, we only had to do 10 potential comparisons. If we had 100 elements, we'd have to do 100 comparisons. So the number of comparisons there is growing linearly, as the name indicates, with the number of elements. Whereas binary search was very different. We were able to cut our search space in half, and we said that this cutting in half function was the logarithmic function. So we said that it grows logarithmically. So if we think about having a 100 element array and using binary search, we're able to cut our search space in half on that very first comparison. So to go from 100 elements to 50 elements to 25 to 12 and so on down the line. Of course, we should say that with binary search we have to have a sorted array, whereas with linear search we don't have to have a sorted array. So what I want to do now is go over to Eclipse and do a basic comparison between our linear search algorithm and our binary search algorithm, just so we can get a feel for really the difference in the amount of work that's going on between these two algorithms. So let's go over there and do that. Okay, so I'm over in Eclipse now, and I've already created a project, and I've also created a CPP file called linear versus binary. And I've pasted in our linear search function and also our binary search function and made a few changes. So the changes that I've made is basically related to keeping track of the number of comparisons that are going on. So I have this count variable here initialized to 0. And inside this for loop here, I just simply increment that count variable each time we do a comparison. And if it turns out that the value that we're searching for is equal to a particular array element's value, then we'll break out of our for loop and simply output to the user the number of comparisons that took place. Now, it could be the case that we never actually enter into this if statement here and break out of the for loop. So I don't know if I've used the break statement before in previous videos, but that's just a keyword in C++ that allows us to break out of some structure based off of some condition. So it's what it's saying here is we're going to break out of this looping structure based off of this if statement being true. So it may be the case that we exhaust this entire for loop before we output the number of comparisons. But that's still, information that we would like to know, because we are wanting to keep track of that, because the number of comparisons really is the overriding operation that's going on there with linear search. Now with binary search, we have something similar going on. We still have this variable called count, And then we have this looping structure again. Of course, with the binary search, we have a lot more going on inside the looping structure. So some of you may be saying, well, you're only incrementing here the count associated with this comparison operation, but you really have, this update of mid, so we have to, do an addition and then division operation. So there is, additional work associated with binary search on each iteration. But again, the main thing that's going on is we have to iterate through this code some number of times. Again, the amount of work is some constant amount more on each iteration, more than the linear search. But again, it's this very small constant amount, so it's really quite minuscule in comparison to the overall number of iterations that we have to do for linear search in comparison to binary search. But it's the same idea. As soon as we find our search value is equal to a particular array element's value, then we'll break out of this looping structure and output the number of comparisons that took place. The other functions that we have, or the other function besides the main function, is this populate array function, and that just simply populates our array with some values. It just populates the array with the values of 1 up to our size, so a very simple function there. And then down here in main, we have a do while loop in which we simply ask the user to enter in an int for the size of the array. We create an array, and then we ask the user to enter in an integer value between 1 and the size to search for in the array. And then we call our populate array, then we call linear search, then we call binary search, and then we ask the user if they would like to run this again. The only other thing that's kind of new here is the sync function. So the sync function basically just clears out our buffer. So if there's any unread characters that we have in our buffer, it clears that out before we call this get function, which the get function will just simply get a character from the console there. So that's what's going on there in the main function. So let's go ahead and compile or build this. So we're compiling and linking this program. Everything should compile and link fine. And now we'll run it. And so we'll start here fairly small. So it asks for us to enter in a size. So I'll say we have a 100 element array, and we'll search for maybe the value of 95. So you can see here with linear search, we had 95 comparisons. In comparison to binary search, we only had 6 comparisons. And you can see that this disparity between the number of comparisons is going to grow as we increase the size of our array. So let's go ahead and run this again. So we'll say type in y here and run it again, and we'll say that we'll do maybe a 5,000 element array, and we'll search for maybe 4,785. So again, the linear search, as we expect, growing linearly, whereas with binary search we discussed how it has logarithmic growth. So we're cutting that search space in half, and we only did 8 comparisons for binary search before we found the value that we were looking for. Let me run it again. So we'll do y here to run again, and this time we'll do maybe a 100,000 element array, and this time we'll search for 97,845, and you can see there that we went from our previous time when we were doing 5,000 elements, we only did 8 comparisons for binary search. This time we went up to 100,000, so a pretty big change there, and we only had to do 16 comparisons. Linear search, 97,845. So you can see the difference there. And let me just show you that I'm going to go ahead and quit this particular program and go back and change up our code. So even if we were to go in here and change up our count here, so instead of doing count plus plus, maybe we do count plus equal 3. We'll say that it's 3 times as costly for binary search in comparison to linear search. So I'm going to change this up too. So we'll say linear search, we'll say linear search cost, and we'll say binary search cost, for lack of a better term, because it's really no longer just counting the number of comparisons. We're just trying to illustrate that maybe on each iteration is 3 times more expensive for binary search as it is for linear search. And I don't even know if that's the case, but just to show you that that really isn't a huge factor, I'm going to go ahead and build this and run it again. So you'll see that is a bigger factor with maybe some of our smaller values. So if we had only a 100 element array and we were searching for the value of 95, we can see, oh yeah, with linear search, still 95 comparisons. Binary search, we had to do, our 95 is the cost, which in that case would be 95 comparisons. Whereas binary search, we have a cost of 18, so that would be the number of comparisons plus, calculating the midpoint and maybe doing some other additional comparisons as well. But if you run this again, so let me do Y here and run it and do maybe 100,000. So we'll do 100,000 here and then do a search for, 94,623. And you can see that we have very slow growth, even though we're doing 3 times the cost amount on each iteration for binary search. So you can see the big difference there. The other thing that we should state again is that with binary search, we do have to have a sorted array in comparison to linear search. It doesn't require us to have a sorted array, and there is a cost associated with sorting something. So, whether you should use linear search or binary search, it really depends. It depends on how many times are you going to be performing the search. If it's only one time and maybe the array is not that large, then linear search may make sense. If you're going to be doing a lot of times, then it may make sense to go ahead and sort the array and incur that cost so that you're not having to search through every potential element of the array to find the thing, in comparison to binary search where you're actually cutting the search space in half. The last thing that I wanted to show you guys before I end this video is just a plot comparing linear search to binary search. So if we look at this plot here, you can see that we have our linear search here in this orange, and we have binary search here in the blue. And I only did it for a very small number of elements here. So this starts out with 2 here and goes all the way to 32. So I was doubling the number of elements for the plots here. So it goes 2, 4, 8, 16, and then 32. So you can see here in blue, with binary search, even though we're doubling our search space, so doubling the number of elements, we only have to do one more comparison. So here we only had to do one comparison here if we only had 2 elements, whereas if we went from 2 elements to 4 elements, we only had to do 2 comparisons in that particular case. So we went from 1 comparison to 2 comparisons. So here on the y-axis here we have the number of comparisons. But you can see here with linear search we went from 2 to 4. We had to go from 2 comparisons to 4 comparisons there. So you can see that every single time that we're doubling, we're also doubling the number of comparisons that are going on. That is not the case with binary search. We have this very slow logarithmic growth, and you would even see more of a drastic comparison there if I selected larger values. Of course, it would start looking like the logarithmic growth was almost flat in comparison to the linear growth. All right, so that's it for this video. Hopefully you have a better sense of what's going on in terms of the amount of work with binary search and linear search. So that's it for this video.